We will study about the discrete time Fourier transform. In previous class, we talked about the sampling theory. Let us assume that here is a continuous signal like a sinc function. Okay, this is sinc function. Amplitude is 1 and this tau. Then this function can be expressed as sinc t of tau. In the spectral domain, by taking the Fourier transform in continuous domain, so that this one is omega. Okay. In the spectral domain, it looks like a box shapes. The peak value is the product between this 1 and tau. So this is tau. And the bandwidth is 2 pi over tau. That's why it is a pi over tau. And this one is minus pi over tau. So this is the Fourier transform of sinc function. What about the sinc square? If you're taking square of this sinc function, t of tau, I take the product of sinc 1, then the shape will look like this one, scale 1. Okay, by taking square, the amplitude is the same as 1, but the first null is also tau. So this is the square version of that one. What about taking Fourier transform of this one? In the time domain, it's a product. Okay, this sinc function is a squared. It means the two sinc functions are producted in the time domain. But in the spectral domain, it happened in the convolution. Okay, we have the convolution of this rectangular pulse. Then the shape will look like a triangular, like that. Okay, this is spectral domain. What is this corner? By taking convolution, you can think about that by taking convolution, this corner will be 2 pi over tau. And this one will become minus 2 pi over tau. And what is the peak value? Peak is the wholly overlap cases. Then this becomes the tau square times 2 pi over tau. So that's why this becomes the 2 pi tau. This is the peak value. So you need to understand the basic operation between the sinc time domain and the spectral domain as a rectangular, or in case of squared version as a the triangular shapes. When we consider the band limited signal, this in sinc square cases, this one is maximum frequency that can be allowed, and in a sinc cases is a pi over 2. This is maximum frequency component. When we take the sample, it means that we make a sample of this one like this way. By making sample in a spectral domain, in the spectral domain, it looks like a repeated version, like that, in the spectral domain. Similarly, it's the same. By taking sampling of this one, it depends on the sampling period. You know that this one determined by the sampling period. We call this one is omega s is 2 pi over ts. Ts is sampling period. That's this time difference, sampling period. Similarly, this one also repeated in this way. So old way repeated in this way. So you can think about in the spectral domain, it's a periodic. Okay, in the spectral domain, after sampling, it's a periodic. Seems like that. The Nyquist zone is corresponding to half of the sampling frequency. We call this one is a Nyquist frequency. This is Nyquist frequency. For the proper sampling, the signal bandwidth should be less than the Nyquist rate. Means that the maximum frequency of signal should be less than the Nyquist frequency. That's a requirement. Here shows that these figures, sampled signal spectrum are given like this way. It is repeated every harmonics of sampling frequency. Every harmonic sampling frequency, it's repeated, okay, like that. And because of that, it is periodic. If we adding the sampling frequency, then it's the same. So spectral domain, sampled signal, it's a periodic one. Okay, so period is omega s. So sampling frequency is the period of that one. And the Nyquist criteria can be understood that the signal is repeated every these portions. Okay, this one is a Nyquist frequency of omega s of t sampling, and this one is a half omega s of 2. This one is a minus omega s of 2. So the maximum frequency component should be inside of the here. So signal spectral component should be inside of the here. Okay, that's the Nyquist criteria. Let's think about the DTFT. This one is a Fourier transform of XCT, continuous signal. Okay, and Fourier transform of a sampled signal can be understood in this way. Sampled signal is between continuous signal and impulse train. That's the sampling process. So sampling signal can be expressed the summation of XCKTS times delta function. By taking the Fourier transform of this one, you can understand the delta function, providing that it is only non-zero at t equals kts. So this t can be replaced by this k times ts. Then that becomes this expression. In this expression, we would like to interpret this part. So that is this one. Omega is the angular frequency of the signal, and ts is sampling period. Because of the Nyquist rate we talk about here, we know that these frequencies are limited between the Nyquist criteria, and if you multiply ts, then it becomes in this way. We define the omega times ts is a small normalized frequency of omega. So we call normalized frequency is this one. So that's this one. Omega times ts is normalized one. The value in between minus pi and pi. We can take a range in this way, but the same, similarly, this one is a periodic one, so we can take in the same way with this expression over 2 pi. It's the same range, okay? Basically this is valid because of the periodicity of this function, as we talk about here. This one is a periodic. So we can re-express this one with normalized frequency of omega, okay, like this way. Then XCKT is just the case sequence of that, and e to the minus j omega n is this one. That is the Fourier transform of this one. Fourier transform of a sampled signal is called DTFT. We express this one is a discrete time Fourier transform. Discrete time Fourier transform. Okay, this is DTFT. In the DTFT, xn sequence is transformed by producting e to the minus a omega n, and okay, here is index should be n. there's no k. So n equal changing minus infinity to infinity. By summing up, we can find out the DTFT, and omega is defined pi and minus pi in between here. And inverse DTFT is defined similarly in these occasions. So we can we can recover the original sequence by taking the inverse DTFT. Okay, and x e to the j omega DTFT over xn. Okay, this one is a periodic with a period of 2 pi. That is the same reason we talk about equation 6.5. If we normalize this one, omega s, you know that omega s times ts is 2 pi by definition. We defined omega s as 2 pi over ts. So this is a sampling frequency definitions. So 2 pi means omega s if it is non-normalized. Okay, this one is Nyquist rate. Okay, this is Nyquist frequency. So we can measure the spectrum from 0 to the 2 pi or minus pi to the 2 pi, minus pi to the pi. But usually we are taking this approach. So omega are confined in between minus pi and pi. But the same thing can be understood by 0 to the 2 pi. We know that after sampling, spectral domain is periodic. So we can taking this range. If we taking this range, it becomes in the normalized frequency it's minus pi to the pi. Okay, that's the Nyquist frequency range. But sometimes we can taking 0 to the 2 pi. Okay, this is 0 to the 2 pi. It contains the same information because it's a periodic. Okay, so we talk about the DTFT and what is the normalized frequency. In the normalized frequency, pi and minus pi corresponding to Nyquist rate, and 2 pi is a sampling frequency.